So let's keep looking at the way we do our calculations with the normal distribution. When we ended Friday last, we were talking about determining the chance of something happening. And really, we were using the standard normal all the time. And we can use any normal distribution. With any average, with any standard deviation. But if we always convert to z-scores, we only ever need to look at one area, one curve. It's always this distribution. So by working in z, we allow ourselves to only ever need one table. Everything can be done in z-scores. Personally, I think that's the better way to do it, but I can have any setup. So on page 249, let's take a crack at the problem they give us. I think we did this one similarly. Talked about the number of calories in an Egg McMuffin. This is problem 31. Did I do this one last time? I don't remember. I'm going to do it again anyway. So we're going to assume the number of calories in an Egg McMuffin is normally distributed, a mean of 290 and a standard deviation of 14. So let me write that down to start with. First thing I know in problem 31 is that the mean is 290 and the standard deviation is 14. Now, again, I'm not a nutritionist. I'm not sure where I'm going to use this. I don't know which of you are on particular diets, whether you're trying to gain or lose, regardless of what you're trying to do. But if I say, all right, what is the chance that I have an Egg McMuffin that's less than 300 calories? Now, again, I can do this in several different ways. I could say, oh, I'm going to use this normal distribution. N 290 and 14. And then I could go into Excel and I could say, hey, this is what I want to do. So if I go into Excel and say, I want to use a normal distribution with mean 290 and standard deviation 14, it is norm.dist. Right there. First thing that comes up when I start typing norm is the normal distribution. And then when I hit the parentheses, it tells me what to fill in. The first thing I should fill in is the x value. I want my x value is 300. I want to be less than 300 with a mean of 290 and a standard deviation of 14. Now, the fourth entry says cumulative. If you put a 0 there, you're using the PDF. If you're using a 1, you're using a CDF. Think about the tables we had in the textbook. In order to find areas, we're looking for areas under the graph, right? So it's up to me to decide, do I want to use table C1 or C2? But both of those, think of areas coming from one side. Before I put in the 0 or the 1, I'm going to go back to my paper and ask you one question that we probably should have started with. Draw the picture. What's the picture of our normal distribution look like for this probability? There's my average, 290. My standard deviation tells me how wide it is, but is 300 to the left or the right of that vertical line? 300 is bigger than 290, so it's over here somewhere. And we want the chance that we are less than 300. She's want everything to the left. Since I want all of this, should I use the CDF or the PDF? Because I'm looking from all the way on the left up. That's cumulative. So now I can go back here to Excel and say, oh, the correct flag to put on the end of that is a 1. That command will give me the answer. 76.25. I'll round to 4 decimal places because that's what's in the table in the back. I just copied the number over. Kind of hard to see, but it's up in the corner on the piece of paper. Now, if I were to have done this using the tables in the back of the book, I could use either table C1 or table C2, but to do that, I'm using the standard distribution. So, how would I adjust this command to be the standard distribution? Mike?
Well, 290 and 14 would be 0 and 1, and then find the z-score for 300.
Exactly. In order to do this in the standard distribution, I need a z-score. So the same calculations we were doing in the standard become switching to z. Okay, formula for z. How do I get a z from an x?
Minus mu over
X minus mu over sigma. Sigma. But x minus the average over the standard deviation. So in our case, that's 300 minus 290 over 14. That's 10 over 14. Now, I'm sure if you give me a decimal for that, $71.43, we can put that in as our z. I can also do this in our table. Oh, wait a minute, 0.7143. You want to use table C1 or C2? Say again? Why? Look at the picture at the top of table C2. It shows the area being shaded in all the way from the left, just like the picture we had that we drew of our normal distribution. So I want positive 7143. All of the z values on this first page are negative. So I flip to the second page of the C table, of table C2, 0.714, right? 714 is going to be between 0.71 and 0.72. 0.71 and 0.72764 something, right? The answer we got? 0.762 between those two, right? But I can also do this in Excel because now I know the numbers to put in. There are two ways to do this. Remember, this command, norm.distribution, requires me to tell it that the mean is 0 and the standard deviation is 1. But that's standard, that's used so often that we can actually get another command, instead of norm.distribution, there's 2 rows down, it says norm.s. S for standard distribution. And now it only asks for the x value and the 0 or the 1 for the flag, because it knows that the mean is 0 and the standard deviation is 1. I don't have to put it in. So here's where we put in 0.7143 and a CDF. Now, why are those two slightly different? Promise there's a reason. Also not a huge difference, right? Difference is in the 1, 2, 3, 4, 5, 6, the decimal place. That's a really small difference. It's like thousandths of a percent. The reason they're different is we rounded. Where did we round? We rounded here. 0.7143 is not the actual 10 over 14. Grab your calculator. What's 10 divided by 14? A lot more decimal places, isn't it? Because that's the same as 5 over 7. That's a decimal that repeats. We rounded it off. And that's why we rounded up slightly. We got a slightly bigger answer, but minuscule difference. Same question. What is the probability? Same setup. What is the probability that I get an X value that is bigger than 250? So, a 250 calorie egg McMuffin would be, I hope, fairly unlikely since the average is 290. You would think 250 would be unlikely. What's the chance it's bigger than 250? First thing I want to do before I do any calculations, I want to draw the picture. Draw me your normal distribution picture. And shade the area we want. Where's 250 relative to that center mark? To the left. Are we shading to the left or the right? Because we want bigger than. Okay, now we have a decision to make. I can't use either of my tables directly, because both of my tables shade area from some point to the left. Either they go, the cumulative table, table C2, goes from our Z value all the way down to the left, and table C1 goes from that value to the middle. How am I going to do this area? Right?
I would use C2 and do everything to the left of 250, and then just do like 1 minus that.
Aha! Because the total area under the curve has to be 1. So this is the same as 1 minus the chance that X is less than 250. I'm going to be pedantic here and say less than or equal to, but it really doesn't matter because the chance of being equal to is 0. But that now allows me to use my CDF. Again, I can do it in Excel, I can do it with the charts, I can do it with a graphing calculator. On here, distributions are hiding here under the DISTR above the variables button. So if I hit second and distribution, we want the normal CDF. There it is, our normal CDF. And it asks us, oh, the low end, well, that's as far to the left as we can go, minus whatever. And notice we can put in our mean and our standard deviation. We don't have to use a z-score here. We can use the x's. So I can tell it I'm going up to 250 with an average of 290 and a standard deviation of 14. I don't have to convert to z unless I'm using the paper table. I hit paste, and it takes that and types it out as a command in the front line. And when I hit enter, it does the calculation for me. That is a really small number. 250 must be way down on the left. That's below 1%. Which means the chance I get what I want, Mike, as you suggested, is 1 minus this number. .78%. 79 if I round up. Now, we could have done this several other ways. Again, depending on how you want to interpret that area. For example, another way I could have done this was to say what I really want to do is say that this area is 0.5, but I don't know what that area is. I don't know what the area to the left of the center is. But I know the area from the right center to the right is half. Total area must be 1. The picture is symmetric. So if I take a z-score here, what do I get? I'm going to call that 8.6 for the moment. Now, if I get negative 2.857, if I use table C2, that'll give me this little unshaded area because that's cumulative. But if I do table C1, that would give me the area from the middle to some point, right? So table C1 would be helpful here, except notice all of these z values are positive, but that's okay because the picture is the same on the left as it is on the right. So I can just use positive 2.86 2.8012345 What do I do with that number? And that gives me 0.9979 versus 0.9978, right? Difference is in the fourth decimal place. It's a rounding error. It's perfectly fine. There are lots of different ways to get the number we want. They all depend on me being able to figure out what section of the picture I want. In the same setting, what is the chance that I am between 275 and 310 calories for my Egg McMuffin? Again, my first reaction, everything involving a probability is an area under a curve. Draw the curve, make a picture, and then we'll figure out how to get what we want. What's my picture look like this time?
We tell them the right issue.
So now we have to decide how we're going to get the area here. Again, lots of different options. But regardless of how we choose to do it, we're going to need to calculate two areas. We can calculate with table C1, we can calculate with table C2, we can calculate in Excel. But regardless of how we do this, we need to do two areas. Why? I can't do the cumulative because it doesn't go all the way. I could do the cumulative and go all the way to 310, right? But that would include this little area over here on the left that I don't want. So how would I get rid of that? Exactly. So what I could really do is I could say what we're going to do is the chance of X being less than 310, which would go from here all the way to the left, and then take away the chance of X being less than 275, which would go from here to the left. And if I cancel those two pieces out, then that gives me the piece I want in the middle. Both of those can be done using table C2, or using the CDF in Excel, or the CDF on our calculator, whichever way you want to do it. Which way would you like to try? I do need to answer the question. Which one do you want?
We don't want to touch it.
Okay, so if I'm gonna do this on the calculator. Distribution button. Second. Distribution. Normal CDF. My upper bound is 310. My average is 290, my standard deviation is 14. So I don't have to change any of the rest of it. Go down and hit paste, and then hit enter again. That's this number. I'll write down 0.9234. And then I'll do the same exact procedure. Only this time, instead of using 310, I'll use 275. Now, since I already have that command entered, I could just call it back. Hit second, enter. It brings up the thing you typed in last. The only number I want to change is the 310. So I'll back up, and over the 310, I'll type 275. I don't have to go back to the menu again. I can, but it's not required. Hit enter. 0.14. All right, I'm going to round that to 1420 because it's 1988. That rounds up. 0.1420. And when I subtract 0.9234 minus 0.1420, I get 0.7814. What else could I have done to come up with this value? What other method, rather than not even using these same calculations? What other calculations could I have done? Because that is what my lower bound is here, right? So what if I made that my lower bound and 310 my upper? Oh, calculator will do it in one fell swoop. 7814. I didn't have my calculator. What if I still need to do this in two areas? I got lucky, the calculator did it in one. Which I could go to the table for this calculation, yes. Table C2 would give me these numbers. That's absolutely true. I could also do table C1. But there's something I need to do to use those tables. What is that, Max? In order to be able to use the tables ever, what do I have to do? That's standard. So I have to switch to Z. I can't do anything on this table in X. Everything on this table is in Z. So in order for me to do that, I have to go to Z's. You're absolutely right. I can get those, but only once I get the Z scores. And again, I can do the Z's for each of these. 310 minus 290 over 14. Or 275 minus 290 over 14. So you can absolutely give me the two Z scores, and then we can go to the table and do exactly the same thing, looking the numbers up on the table. 310 minus 290 divided by 14 is 1.4286. 275 minus 290 over 14 is negative 1.07 0.114. Now, our Z table only goes to 2 decimal places. So here I'd use 143. Here I'd use 107. And now you have a choice. You do table C2 or do you do table C1? Because you can do it both ways. If you want to use table C1, this is already in table C1 because that's a positive Z. But this one's got a negative Z, so I'd have to flip it over. And then I would be adding the two areas together because one's on the left and one's on the right. I'd add them up. If I use table C2, I'd still be subtracting because one is on the left and the other one's on the left as well. Questions? Often, we want to go the other way around. Find me the X. What number is the correct value? So to work this backwards, I need to start with the area and figure out what the Z or X score is. Quite frequently, we're doing not the area between two values, but either the area bigger than a value or smaller than a value. Sometimes we're looking for the middle, but more often we're looking for the edges. So we could say, what's the bottom 5% or the top 5%? Here on page 249, a table. Now I must tell you, I don't have this table memorized. I don't remember very much of it at all. What I do have is the procedure by which I get these. This says, find me the highest 5%. All right. Let me see if I can figure out how to do that. Okay. I'm going to draw the picture. And I'm going to say the highest 5% should be somewhere up there. And this time I know the area is 0.05. So let's think about this. If this upper area is 0.05, then this lower area is 0.95. Grab your CDF table, table C2. And in table C2, I'm going to try and find a Z-score of 0.95, or at least as close as I can come to it. So I start looking at areas. And I say to myself, look, all of these are like in the 0.9 range. Where's 0.95? And I notice that right there I have 0.9495 and 0.9505. So 0.95 is right in the middle between those two, isn't it? So right in the middle here, that's where I want to be. So that's 1.6, halfway between 4 and 5. So this is a Z-score of 1.645. If I ask for the highest 10%, How would you find that? So I grab my CDF chart. I see the same picture, right? Only this time, the area is 0.1 here, so this is 0.90. And I start looking for 0.90. Well, if there's 9.5, I got to go back a bit. 9089898990. Okay, here we go. It's right between those two, isn't it? I'm going to go with it's closer to this one than this one. So I'm going to go with 128. 128. But that's a z-score. Z-scores seem obtuse and weird, and they don't seem to have practical relevance. So let's take this same question and put it in the setting we were just in. We were dealing with Egg McMuffins, and we said that they had an average calorie count of 290 and a standard deviation of 14. So the top 5%, the fattiest McDonald's Egg McMuffins, have how many calories? Calorie count was an X value, not a Z value. So I need to switch from Z to X. I'm still going to use the exact same formula. Only now the number I know goes over here. So the fattiest 5%, the most calorically expensive Egg McMuffins, have a z-score of 1.645 or bigger. Now you just have to solve for X. Which means the first thing you do is you cross multiply by 14. 1.645 times 14 is 23.03. I add the 290. And I get 313.03. So the top highest calorie Egg McMuffins have a calorie count bigger than 313 calories. Regardless of the scenario you are working in, the setup is the same. Once you know what z-scores you're looking for, you can find the appropriate X value for the setting. Problem number 43 here says the weights of newborn babies in Foxborough Hospital are normally distributed with a mean of 6.9 pounds and a standard deviation of 1.2 pounds. How unusual is a baby weighing more than 8 pounds? You start at the beginning. The weight of newborn babies. Foxborough Hospital is a mean of 6.9 pounds and a standard deviation of 1.2. How likely or unlikely is a baby whose weight is 8 pounds or more? What is the probability of 8 or more? So X bigger than 8. Now I'm actually going to do this with the z-score. I'm going to do this with the standard normal. So if X is 8, what's the z-score that goes with 8? Now, my first reaction, is that unusual? I don't even need the area yet. We had a definition of an unusual or an outlier piece of data based on the z-score. What did it mean for a data value to be unusual?
More than 2 standard deviations.
Which would mean my z-score had to be bigger than 2. Is this unusual? No. And if it's not unusual, it's certainly not an outlier. So it's not very unusual for a child to be with a birth weight of 8 pounds or more. How unusual or not unusual? I need the area. The probability of Z being bigger than 0.9167. All right, wait a minute. How are we going to do this? How are we going to look this up? What's the picture look like? What I want is this area out here. But we know in terms of Z, these are X's. In terms of Z, this is 0 and 0.9167. How do I get this area? So this is the same as the chance that Z is bigger than 0.9167, which is 1 minus the chance that stuff is less than or equal to 0.9167. Well, now I can go to my table and I can look up the Z of 0.9167. Wait a minute. My Z's are only 2 digits, so let's use 0.92. .92 is 8212. Subtract that, 1 minus 0.8212, and you get 0.1788. So the chance of a child being born with a birth weight of larger than 8 pounds in this hospital is 17.9%. Not all that unusual. One of the things that is important about measuring birth weight is babies that are extremely large or extremely small need to be watched. Babies that are very large usually indicate something with the mother, like gestational diabetes. Babies that are particularly small, we put in the neonatal intensive care unit to make sure that they can come up to a full birth weight. Sometimes that's related to premature birth. Sometimes it's full-term children that are undernourished for some reason. So, what is the 95th percentile in weight? What babies are at the 95% mark? What babies are at the 5%? Now, fortunately for me, I've already done this calculation. To get the 95th percentile, I'm looking at a picture that looks like this. And if you look back in your notes just a little bit, we already drew that picture, didn't we? What was the z-score that we came up with for this mark right here? Right. If this is 0, then this was 1.645 as a z-value. Oh, so to find the 95th percentile, I have to solve that for x. What changes if I want the 5th percentile? Because that would turn this picture over. The 5th percentile would be the exact same picture on the other side. And that would simply make this negative. Then notice what happens. In that top calculation, when I multiply 1.645 times 1.2, I get 1.974. So x is 9.974 pounds. Here, when I multiply, I get x is minus 8 is negative 1.974. So when I add 8, I get a number that's lower than 8. A sign error here is an easy mistake to make. But I want you to think about this. If the average birth weight is 8 pounds, then the low end, the 5% mark, should be under 8, and the high end should be above it. I gave a question very much like this on an exam last year and got those numbers reversed frequently. It's important to note which direction you're going. We will use this a lot in the next idea, which is about sampling. However, this is chapters 5, 6, and 7. We've covered a lot of stuff on distributions and probability. That's more than enough, in my opinion, for an exam. That means We've just finished what I'm gonna cover in chapter 7. There's a lot more in chapter 7. Normal approximations of binomials, other types of continuous distributions like exponential, triangular, and other things that we're not gonna do. If you're interested, I would love to talk to you about it. Come talk to me off-site. Otherwise, this homework is due 2 class periods from now. But what's Wednesday? So on Wednesday, we're not having class. So 2 class periods from now is Monday. This homework is due on Monday. The exam is Wednesday, the 26th, a week from this Wednesday. I will see you all on Friday. If you've got questions, come bug me between now and then. Have a good one.